Hello. Let's see. Good. Hello and welcome to today's live stream. It's been a while. It's been at least 5 months now since we did a live stream. But today we have some exciting stuff we want to do. Some demos I want to show you. And um, for those who are joining us today, usually we've been doing live streams ever since last year. We started last year, and mostly our live streams to just stream um, some of the products we do and some of the stuff that we are building and the research that we are doing. So, uh, previous live stream had were mostly like coding and also demoing some products, but today will be a bit different because we'll be going through some materials that we've been gathering since last year, and also I'll be showing you one of the product that we launched recently, and it's really exciting. So welcome, and happy to have you uh, join the live stream. So first of all, I'll just create some list of what we'll be going through. Mostly the list will entail what the product is, why it exists, and who it's for, and who will mostly gain from using this product. And and then after that, we'll just go through the list and show you some of the features that exist for that for that project for that product. And then after that, we will do a demo of how it works and how it looks like, and also um, show you the deepest of functionalities that you might not recognize easily when you look at the website or the system when you launch it. So the first thing that we will let me just okay. Okay, so the project, an introduction to the project is so Neat is the project. So the project is really just so if you are a programmer and you've used programming tools before, usually editors, and mostly the most popular of these editors is VS Code. And for other people who have VS Code, there is also PyCharm. There is also what else is there? There's the newest versions are Anti-Gravity by Google, and also there is which one is this? Casa, yeah. Most people know Casa, but what we have here, right here, is a bit of all those IDEs, but then it's a bit different in the sense that our editor is Vim based. So if you are a Vim user or you ever used a Vim editor, then Neat it takes all the features from not all, but some of the features that are mostly used by programmers from Vim to Neat. So if you are a Vim user, then Neat will be some one of the tools that you would be interesting for you, and we'll see why that is. So a bit of like that's like a bit of the introduction, but it's not just an editor per se, because what Neat provides is more than an editor, in a sense that uh, it brings to you what we call in the world today, what we call agentic orchestration, or agentic coding or something like that, right? So you have agents, and these agents need to to okay, we'll be used to IDE where agents are uh, like IDEs come with agents, right? And mostly it's a black box. So like the agents are not really like you just have to configure what the agents are. And so if you've ever used Casa, you've ever used anti-gravity, it's the best tools so far in the world currently, the best IDEs for in the world currently. But these IDEs are fine, but they don't offer the programmer. So if you're a programmer who likes to play around with, you know, your 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 editor, you like to move like you Vim offers the functionality for you to stay in the zone always. You don't have to, move cursors around and try to find whatever file you want. All you have to do is to keep your fingers on the keyboard and then just punch the keys and code or move stuff around just on using your keyboard, right? So this is why this is how Neat works usually, and we will see that. So I'll show you just what the features go through the website and just introduce the features, and then we'll go through. Oh, sorry. Show the website. Sorry, I'm writing this now, but let's go. Show the. Yeah, I had trouble setting up this because it's been a while since I did live stream, so just I'll just write stuff. So show the website and introduce the intro the features. And so that's like one thing we will go through today. And the other thing will be talk about the thesis, like why neat and what are the things that are included in this in the editor. So we'll do the thesis, and then we will do um, then we'll show demo. Like these are like the three things we just go through. It's not much, but we'll walk through all these things. So the first thing to look at is the website, like which talks about what NEAT is, and from here you'll see example of screenshots from Neat. So these are the like the hero image. And if you look at the interface, this is how it looks like. I'll talk about all these things right here and what they mean and why they are good and they exist. Then I'll talk about this all these pens and the editor itself. And then also talk about multi-pane. So multi-pane is a nice feature in Vim if you are a vibe coder and you don't want to like um, just open many terminals around. You can open just one terminal and then launch multi-pens, and those multi-pens can be set up in a way that each pen is essentially a session itself in itself, right? So that's one thing we'll go through. And then so so the end goal of Nate is to just be it's just to be for programmers to to code and also use agents. So so the goal of Nate is to not strip away, the programmer or remove them from the picture. It's to give them that power to interact with agents as well as code with the agents as they go, right, as they do their work. So this is like a simple video that shows um, how to like open up stuff, see what exists, search for files or whatever you're working on, right? And then so the features, so these are like mostly the features that exist. So we have Vim throughout, like it's all Vim, and then not all Vim like you if you don't know the keys, or you're not familiar with how Vim works or how the keys are, you can use the cursor as well, so that we don't like remove that power, or remove the other user who does not understand or has never used Vim. So Vim is there, but you can also do other things like use the cursor and move stuff around using cursor. Then we have a agentic station. We also have shadow agents. Shadow agents here. So agentic station is where you will manage your missions. I'll show that in a bit, but this is where you manage agents and their mission and assign roles, and then select which agent or backend you want to use with the Codex, Claude, or Gemini. Those are like the currently available backends. And then we have shadow agents. Shadow agents are like the agents that run, but they don't really appear in the front end. So they just run in the back end. And these are usually just for augmentation. So the shadow agents, they mostly run on a single. So if you're only running a single lab test, or like just running one single mission or one single agent, then that agent needs a way to say augment it. It's a way of augmenting the agents, but then that agent, so that they can perform better when they are doing coding or they're doing research when using Neat. So we have the shadow agents, and those agents are launched based on like the prompt. So if you submit a prompt to the agents, that prompt will be augmented by the shadow agents. So they go through the system, and then they create a way of an awareness to the agent that you've submitted the prompt. So awareness in the sense that it gives the agents what exists in the system, and what the environment looks like, the state of the environment looks like throughout the system before the agents can act on your prompt. So that's what the shadow agents are doing in the system. And then we have um, Swarm, Swarm orchestration, and these are like, so some are like you can run multiple agents at the same time, and either parallel or bulk, or just you are doing a single agent, but then you want them to run in Swarm separately. Then you can issue a command, and then it will run an orchestration, a swarm orchestration of those agents inside Neat. So that's the one of the feature we have, and then living substrate. So we figured out that if you have a system that runs and you want it to keep running, like you can leave your system in a loop, right? But then currently, I don't know if there's a system. I mean, there are other systems that do this, but then if you leave the agents and then try to come back and talk to the agents, they sometimes go off script, or they just go off the context. Like they lose context of the system, they lose the state of the system, the previous state. So what the living substrate is, it creates like a copy of the state of the environment at that moment. And then when the agents exist, they will come back and query the environment through that substrate. So the substrate will be like a database of the history of what the agents have been doing. So agents leave traces, and I'll talk about how agents communicate throughout Neat. So you can have many agents talk to each other, and one of the ways Neat provides for those agents to communicate with each other is this feature of living substrate. So the environment, in a sense, is assist a place for agents to communicate with each other. And the sort of communication we use on in it is the if you guys know about this stigmagy. It's called stigmagy. I'll just look it up. Stigmagy is a form of communication where agents can leave traces inside the environment, and they don't really directly talk to each other via messages like the way humans do, or some agents do, like they send each other messages to communicate with each other. That's not how Neat does. So Neat uses this stigmagy mechanism where agents communicate with each other through leaving traces inside the environment. What we call the substrate is the environment. So the substrate keeps those traces from agents, and I'll talk about the traces that are kept in the environment. They're simple traces, they're not complicated traces. Uh, uh, like whether done markers. So if an agent finishes some task, it will leave a trace that I'm done, right? Or it will leave a claim markers. Claim markers is if you're working on a file as an agent, you can leave a claim in the environment saying that I'm working on this file, right? As a marker. And other agents see that, they will not touch the file. So that's a solution to the problem of uh, multiple files, multiple agents conflicting with each other because they are working with the same file or something like that. Solutions have been there, they exist. Like locking files is one of the solutions that most some editors do. But for Nate, we just keep traces in the environment so that agents know which is which. And that's like what the living substrate does. So stigmagy is a technology or mechanism that is used by ant colony. So if you study ant colony, you'll realize that they there's no way they can communicate by sending messages to each other. So they sort of some send. I don't know what the scent is called, but it's um they leave traces by like I don't know, some scent that they leave into the environment, other so that other ants see that, or um, use that as an indicator of like information, like that's like information to them. So that's one thing that Neat does. And then artifacts. Artifacts are the things that agents produce. So an agent will do its task, finish, and once it's done, it will output an artifact of what it has done and why it did what it did. So that's like we keep those, and those are like divs in code, and also text, like it can leave text. So that's one thing agents in Neat do, or one of the features that Neat provides. And then we have game of life lab. So game of life is one of the biggest feature on Neat because it's we are using it as a fitness function for scoring agents code, right? So agents will write code. Sometimes it's badly written code. And so to figure that out, like to figure how or why it's bad, we run it through a system or a fitness function through the game of life as a fitness function, where the game of life converts the code that the agents has written into bytes or um, actually into tokens or bytes. So those bytes are uh, interpreted as what the cell or the seed to the game of life. So you run the seed and figure out which how long it lives, or what sort of artifacts or uh, structures the game of life produces through that seed. So we'll talk more about that, but I'll just run through quickly these other ones. So game theory, you can run agents to play with each other. Then we have GPU acceleration if you're on Mac or mostly Mac. So if you're on Mac, there's Metal GPU. You can use that to accelerate um, simulations. So I'll talk about simulations too. Syntax highlighting, not important, but syntax highlighting is one of the features we have, and an inbuilt syntax highlighting. Then built-in verifications. So we verify whether mission is complete. Mission is each agents of multiple agents have work on a mission. So the verification process of verifying if whether that agent or that mission is complete is it's a built-in process that Neat does. And then we have security. Security is so Neat is secure by default, so we don't really do network. We don't run network commands or anything that through the network. Only the agents that you add to Neat, and I'll talk about how to add the agents. You don't really add it using any method. You just have to install agents normally from, if you're using Cloud, just install Cloud, and then once you launch Neat, it will pick, uh, it will look into your executables and try to find which if Cloud exists, then if it exists, it will pick it automatically. So no networks. And then we're in tech classifiers. This is another is like a shadow, but then it's not a shadow agent. It's an intake. It augments your prompt before it sends to an agent. So if you are an operator and submit a prompt to an agent, the intake classifier does an augmentation of that prompt before it does submit to an agent. And mostly it does. You don't lose operators information. It just augments it so that the agents are aware of, like, if, link the system and the prompt, or the code base and the prompt the operator submits. Then this is, I don't know, this here, but the idle sleep is just, you can run agents while your computer is hibernating or something, so the agents still run using when you run them on it. And then, so terminal, if you don't want to run agents via Neat, you can run the terminal. I'll show that in a bit, but you can run the Neat. You can launch terminals in Neat and run your agents. So those are the features and breathing subset. I've talked about this. You have claims, signals. These are the things that are left into the environment by agents so that other agents can read them and understand and also act on them. So we have those, and then roles. So these are these are roles for helping agents into the environment and understand what each other agent is working on and what it does, and resolve conflicts if they are, or an observer just reads the entire state of the environment and has like the context of each other agent's works or whatever they are doing. So the observer does that, and resolver will resolve any conflicts if there are, and then the worker is just the agents, right? Like the one the one who's doing the work. And then the orbiter is a collective actors, like they just walk around the system and collect information around, right? And then so these just skip threes. and the code is live. So one of the features we have and one of the motivation for Neat was how can we build a system that allows agents to write better code, right? If you've ever written code with an agent, or if you ever use an agent to write code, you realize that they do mostly append to existing code, right? They can append, and most of the time there's duplicates, and then you'll find that if you ask an agent to fix something, they usually just append, like just find something else, like they'll do another solution, but then append that solution to the existing one, which creates mostly dead code. And you realize that once you finish a file, or once an agent has finished working on a file, it's this giant file that you can't even pass it. You can't read it. You can't understand what's going on. So that's one problem that we are solving with Nate. And the solution we have proposing is, what if you had a fitness function for agents to score their code? So you have um, I write some code as an agent, and then this code is good. It works functionally, is fine, and it passes the test. It does all the what the it does it goes through all the processes, styles, and all that stuff, and passes the functionality so well. But then the question comes to, is this code structurally correct? Like, is it clean? Is it clean code? Is it um, humans have been doing this for many years? Like, you have to review code, you have to um, uh, run through linters and all that stuff. But then for agents, you can do that manually, but it takes time. You don't have time to waste on like reading agents code and telling it like this is change this to this. So what we are proposing here, which is experimental, but we've tested it and it seems to work, but um, the proposal is that we have a fitness function, we pass code through that fitness function, and then if the code is um, is um, is good or structurally clean, or structurally quality in terms of quality is good, then we the fitness function will score it as good, right? It will produce a function, or it will produce a number that will identify the score to that code. And the fitness function we chose is because code is something like, if you write code, you realize it has some structure, right? If you read code, or if you've ever studied syntax highlighters, you realize that they have some sort of structure in them. So utilizing that structure, we decode or encode that structure into a seed, or to a seed, which we then feed it to Conway's game of life as a seed to the cellular automata. So the cellular automata runs that structure, and if the structure lives long enough, then what we will call that is like, we will interpret that as um, good structurally written code, right? And the process is simple. Like, you write code in your editor, or agents write code in the editor. We pick raw bytes from the open file, pass it through the encoder. The encoder, we use four encoders that I'll show down here. These are like the scoring encoders. So that once it's passed through the encoder, we pick the value of the grid. so that the seed of the encoded file or the structure is fed into the grid, and that and we do other things like detect jitters and threshold, and I'll show you how the threshold is picked. And then we convert this structure into a symmetrical thing. So symmetry, we put them side by side, the structure, and then we make a symmetrical version of the structure and run the simulation in NCA. And then once we do that, it will produce a value, and that value will be the score for that code. So if the score is greater than the threshold, we get what we call a score for that specific code. And agents sometimes will write code and then they run to the system. It fails. They retry. So there's sort of a loop. So that's like I don't want to go much into this, but the fun part would be just to like talk about the thesis, which is also something I've already talked about, but it would just be like talk about the system, these four encoders that code the code, and also go through a bit other things. So um, and there is a challenge. So the challenge is um, can your code survive in a sense, like right? So I'll I'll just I'll just talk about these two, the tire for ranking your code. We have still life. So if you have ever seen a game of life simulation, we have this kind of structures, still life, where the system or the cells are just still, right? They're not changing or moving, right? The oscillators are other things, so it's mostly they oscillate around mostly. So it's a repeating it produces a repeating cycles that oscillates around all the time throughout the generations. So that's measured for complexity encoder mostly. So these are like the tire. So every time your code hits any of these tire, we say it's good or bad. So still life, it's mostly like bytes code is it's all over, right? Like it's if you think about starting a grid with a random cells, right? Just pick random cells, and uh, most of the time uh, it produces just still life, right? Because there's no structure, um, there's no way that that code will produce anything interesting, so it's just still life. And this is the code that most agents write, I think. Well, yes, because we've seen this before, and people have currently, even if you use Nate, the starting point will always be still life until the agent retries and retries and retries and gets to spaceship. So most of the agents that have used in Nate have been around spaceship, and a bit of like Methuselah is they live longer. So the code lives a bit longer because it produces structures that live a long time before they die out, and sometimes agents get to these, but it's a difficult tire to obtain. So, and this is the highest of the tire, and it's really hard to get there. So agents have not figured out to get here, but the goal is to for agents to learn to get to these, right? But then the problem is that the problem mostly for most editors is agents can always find a way to game it, right? And what Nate has currently is so if you so some agents will try to game it so that they get to replicators or Methuselah, right? So the um, the anti-game uh, metric we use is this parsimony. So parsimony is, so if you if you have ever looked at some code and it has um, blood, it's really just blood comments, doc string or function is so big, or like such code. We call it spaghetti codes, and that kind of code is what mostly some agents would produce. But then, uh, since it's running through the system or on its system, it's always, or the agents always try to do that uh, through gaming the scoring matrix to get to replicator, because that's the high scoring tier, right? But parsimony is the one that penalizes such agents, right? So if agents do just add or appends code, or leave code around, or comments unnecessarily, comments to code, what the parsimony detector does, that is detects that structure or that specific gamification, and then feeds back to the agents as a penalty or punishment, so that the agents can retry. So that's one way to remove gamification. And then with other ways too. So this is like um, I think the most efficient way Neat has, but I'm sure there are better and more efficient ways to do that. So that's like an introduction to the challenge. But I'll just go through the thesis and talk about. We'll have like 15 minutes to talk about um, the demo, right? All right. So the thesis. So I have a blog post um, on everything here, right? So what the problem is. So here I'm just talking about what the problem is, and mostly I'm talking about I'm introducing the problem. And the problem is that agents write code, and mostly the code that is written by agents is usually poorly written code, and they just do that and keep doing it, keep appending code whenever a new feature is presented to them, or a new bug um, has been given to them as a prompt. They will just keep appending the code, keep appending to the code base until they solve the problem. So that's one problem that we have addressed. The other problem is that we have vibe coding as an everyday thing for programmers nowadays, right? People vibe code every day, and most of the systems or the tools they come up with they usually decay faster. Like you can build a system today, and it decays, or the code, because agents wrote the code. You go back to read the code, and it's a mess. So you can't even understand it. You can't even build um, upon it, or add new features to the system, because it's it's code that has been written in a way that to finish or to ship faster, right? But that's a problem, because when people ship code and then it decays faster than it can live, right? What really happens is that if a new product or a new idea comes up, or people wants something else that should be built to replace the old one, they just do that. They keep doing it. They will write code, use agents to write it, and at the end we have so many products or so many systems or so many tools around. Most of them are not used, or most of them um, just exist but are never like getting any better, right? So you when you need a better thing, you build it and replace the other one. So it just creates an exponentially um, many and many tools that exist that most of them have been forgotten. So that's one major problem that needs is trying to solve. So it's we're calling it the population problem, which is like so many software will exist, but most of them won't be used anymore because we cannot maintain them anymore. Agents have written code. It's unmaintainable. It's hard to read. It's really just bad, right? So um, we are trying to solve that in the sense that we build a system that actually lets agents to score their code, and by scoring, agents get better and better and better, and it doesn't just build better systems or better code, write better code. They also learn to write code. So agents who write code use the Neat as a tool for writing code, and what Neat offers to them is you can learn to program or learn to write good code. And at the end, Neat agents will be better at writing good code, right? They learn faster at writing the code itself, and then they will evolve. Like they keep evolving through measuring their code and scoring it as they write it. So that's basically the idea, and the whole um, why need and the whole thing about uh, what how we are scoring the code. So this figure shows like two example of random seed and a structured initial seed, right? This is like a structured, popularly known as R pentamonies, right? It's one of the it's one of the Methuselah um, structures in cellular automata that lives longer, or in game of life that lives longer, right? So we have two structures. One is random, one is a structured two grid. One is randomly selected bits, cells, and then one is a structure that is picked because it's known that it has been studied, and it's known that it lives longer, many generation. And you run a simulation, or just simulate for a 500 generation thing. Yes, so you run this for 500 generations, and then what you get is yes, so what you get is the gray one is the random version, right? It starts up here, so many live cells, and then decays, and at the end it just decays. But then you start with a structure, with just one this structure, a structured system, and what you get is the system keeps, um, the generations keep growing as you go, right? So life cells keep growing as the generations go. So, and then you get that it surpasses, or sort of they cross over, in a sense that the one that was structured beats the one that was unstructured, right? So this is um, the whole idea. Like if you have good that is structured, if you have good code that is structured, chances are that through our fitness function, that code will live longer than unstructured code. And then this is like a simple evolution after those many 5,500 generations. You'll see that the structure that started out really simple is has so many live cells, and the structure that started out with so many live cells, it's decaying. So that's the whole idea. Like good code live longer, and bad code just decays. And that's the whole theme, like the whole Nate's point of view, like Nate's trying to do that. Like we want to be able to have good code written via Nate. And we have just encoding pipeline. These are simple. If you want to understand them, can go read through the code. And we have also these encoders, so different structural steps. So we start off with take your code, convert it into tokens or just bytes, and that code is fed to an encoder. This is fed to an encoder. Then that converts to a grid. Then we we apply a threshold. And to understand what that threshold is, you can read through this blog. And then we apply the symmetry. So if you look at these, this is a structured code. Then it's applied one is it yeah 180 degrees, and then it becomes a symmetrical 90 degrees. Then it becomes a um, symmetrical structure. Then you run a skier, you run a game of life cellular automata against this structure, and from that you get measurable output from the agents or the code, and that agent we keep the results of the CA as genome to the agents. So the agents will get that as feedback, and then we feed those to the agents, and that feedback is how they learn. Like how do I make code that is structurally good and can live longer? And then we have four encoders, token spectrum. To understand what these are, you can go through the blog because of time. And what I would just also, so these are the experiments, some experiments we've done, a simple file that was refactored using Neat, and the output and the results, and what these are like. These are like the metrics, the values we feed to the agents to score their code or to learn from their code. And then we also have so the life cycle is have agents, the planner, we have proposers, then we have the judge, integrator, which is the writer, and then we have the verifier. This is the simple structure, but it's deeper when you look at you play around with it itself. But this is like a simple version of the architecture of how we run the agents. And so that's so if you interested, I've linked this blog into the live stream. You can go through it and understand. But what I want to take us through is the Nate itself. So if you install Nate via get started, and you will install Nate. A disclaimer, so Nate is token hungry. So if you're running multiple ranges, they consume tokens like so bad. So yeah, that's one disclaimer, but you can install Neat, check before you install. And once you have it installed, I'll just launch Neat because I have it installed already. And so this is the layout. When you install Neat and launch it in directory, it picks that directory, and we have the agents chat. You can chat with agents, and we have backends right here. So these are the backends that exist in it. So Codex is available. You can use Codex agents. You can use Cloud agents. Gemini is just for display. We haven't put or implemented Gemini as a backend, live backend. And then, so to use any agents, you can, use if you're Vima, like you can, use your key, your keyboard. And but if you are just, you want to select, you can select which agents you want to which backend you want to use and the agents you want to use. And then templates. So we have templates, which is you can for lab template is you just want to communicate with one agent with shadow agents. And then for parallel, you will have things like if you select parallel template, you have things like roles. So you can select these, and then the main agent will have roles. You can pick which role the agent would use. Then we have bulk, and also we have missions. So these are like the existing four missions or three missions. So general mission or automatic, it just picks based on your prompt. But then you have research and computational research. So if you are doing research in computational research or just general research, you can select either of these missions. For now, I'll just pick auto, and I'll pick lab. And what I'll say here is I'll just tell the agent to, so I would like to just launch an example of some, I want to run 6 agents, right? And in parallel. And then I want to tell them to, let's see what we can refactor, maybe utils. Uh, this, yeah, I'll try to say, so refactor creates neat to and source cloud pool trace. And you can add do not build functionality, but this is just a simple prompt. And once you have configured your agent, and then you can launch the prompt, and then what happens is the planner starts because you realize these 6 agents, a clone of this clone of the main agent, some clones of the main agents were created, 5 of them, plus the main agents make 6. And those the main agents runs alongside the clones. So what happens here is that the main agents will plan. Usually, just takes some minutes to plan because it has to go through the files, read through the project at first. And then once it has finished, we'll see that each of these agents will be assigned a role once it's done. So after the planner has finished, each of the agents here will be assigned a role. You will see that in a moment. But while that runs, so these are waiting to to receive their turn. So they won't work until the planner has already finished. And then what you see here on the right is we have this is the seed of this file. So this file currently looks like this, and once we run through the encoder, what you see is that it generates a seed of the bytes, and then you can change which seed you want to, like I can change the seed from the visual, just the tokens, and you can see the visual how the symmetry is applied to that seed. And then once you have done that, you can run this here against this file and see how as an operator you can still see how uh, the evolution or the simulation performs. I'll show that in a bit. But what's interesting is that agents also run through the CA, go through the CA, run their code against the CA and measure it. But from these below the right is the code structural quality pane. So this is like the measure of this piece of file. This is what you see in the currently opened file, right? But you can also, let's say we say pick a different file. We'll see that it produces a different structure right here, and it also produces a different score right here. So these are the four encoders. So the four encoders consistency just means that these four agree. If they don't agree, consistency goes lower. But if they agree, consistency goes above. At this point, it's they mostly don't agree much, but it's not really bad. Uh, and so they really don't agree much here. So if it's more than 5.5, then you get that the agents agree a bit more, agree much more. So and then what else? So what we are seeing here in on the um, after the encoders, the density, so the density of the tokens, so this is still very low. And what it says here is that the generation for each of the token encoders is this value. So this shows the generation and the peak values where when the generations peak, and then what the state is. Is it collapsing? Is it stable? Or the is it surviving? And the cycle period is when the cycle terminates, when the simulation terminates at what period. So periods is we it's detection of the cycle. So in a sense that we detect repetitions, and once we detect a repetition, we know that the simulation is in a loop or is in a cycle. And the identifiers and all the cognitive complexity is also this measurement or statistics tells you how your file is structured and how it's performing based on the measures we have provided or the measures that exist in it. And this data is fed to agents while they are working. So once, and mostly they are agents so we have writer agents and we have just read-only. So read-only agents also see this data so that they can give more information to the writer agents. The integrators are the writer agents which write code or write to the directory or to the project. So this is like the measure, and then you can see files that have already been scored. You can evaluate the genome for the remaining files. So we have 96 files that have not been evaluated. So if I run these, it evaluates those 96 files. So you can see that um, some files that have excellent, we can look at this file, excellent structure are these files. So the function is clean. It's then there's no bloat at all, right? This is like good code, right? I'll call it good code in a sense. And the simple functions, not long ambiguous functions, and it's understandable. You can read this code and understand what's going on. And I think the syntax is, yeah. I mean, this is just which one is this? This is Rust code, but I mean the syntax is needs a bit of improvement. We are using Rust Tricita for syntactical um, work, but yeah. So this is the scores. It produces the score for this file and tells the agents where which function is breaking based on these statistics right here. Tells the agents that this function is breaking, needs to be fixed. Once the agents see that data, they can act on it. And uh, so that's the file scores. Now, what I want to also show is if I run, so if you hit Control Enter, it will run the simulation of this, right? The CA. So if I do that, it will run the simulation of the CA, and you can see that the symmetry of these, and you can just observe your code in a sense that the structure is encoded, and you can see how the evolution works. The symmetry creates structures like these, and like this is one structure. But look at this. So this is still it's a structure, but it doesn't. Uh, okay, so this let's see what this does. This is a glider. Glider is going. It's one of the famous um, structures in Game of Life, and so you can observe the system until it terminates or it hits a cycle. And once the cycle is hit, you'll see period of that cycle right here, and then number of generations, alive cells, how many alive cells exist, and then number of generations right here in the rule. So you can change the rule however you like. So I'll just close this and think it's let's see, how do I change the rule? So the for help you shift and then question mark. You see how you see uh, um, the help thing. But then for rules, I'll just issue a command and see the rules for the CA. So all these rules exist. We have Conway's Game of Life, we have Dry Life, we have Vote, we have Long Life, we have Dot Life, we have so many. We have Labyrinth, we have Molly, Diameba, we have Life 34, Seeds. Like all these rules, you can change them and let the simulation use the rule that you've selected. Now the other thing, okay, so the agents, the planner finished, and one of the things you can do is just click the artifact of the planner and see what the plan looked like. And you see that the agents were assigned roles, which agents, which files, dependency, which agents. And one thing we use is a DAG system. We use this, let me see, it's called DAG directed acyclic graph. Um, Acyclic graph to control dependency. So which agents depend on what, which agents, and then that will be the dependency. So if there's dependency, you'll see debs with something, right? And in this case, I think so we have these agent dependencies are proposer arc minimum genome. And this agent has also judge synthesis as a dependency. So you can read the plan and see what the plan is. And the good thing is you can go through, you can get the artifact it's stored into the system, so you can come back later and view the artifacts right here. So if I go to the agent operations, we have missions, agent still running. We have missions. The mission that is running is mission 001. We have the DAG. You can study the DAG, how the agents are assigned. Then the artifacts. So the artifacts, if you hit R, it will pop up, all the artifacts you have ever used. So there are quite a lot in my case. So all the artifacts, you can revisit the artifacts. And these artifacts are good in a sense that agents can use those to see what work has been done before. Then MCPs, we currently don't have like external MCPs. We use what we have is Claude MCP exists. So I think Codex doesn't have MCP, but there is a executable for Claude MCP. So that's what we use for Claude, and that's for um, when we are doing substrates, or we are feeding information to the agents, or the traces in the environment. Does that we use the MCP, or we use direct call to the agents or to the backend. Then alerts are just informing you what's happening. And this is like Nate's way of measuring criticality, what's happening in the system. And right, so Scratchpad, you can write stuff that you want to implement later or whatever. And what I want to show you is so the artifact. Okay, I told you about the artifact. One thing is, okay, so for if you are the programmer and just want to write code yourself as well, you can use vim-keyed. You can do whatever stuff you want to do. You can search for files using Control P. You can search for which file you want to open. It's fast. And also you can preview the file before you open it. If you want to search for something, you can do fuzzy search, Control F, and maybe I want to search bulk. I'll see that all the files that have bulk. So it's a good way to search stuff. You don't have to go to the terminal and try, uh, grep or whatever. So that's inbuilt in it. The other thing I also wanted to talk about is the terminal. So maybe you just want to run Claude on terminal. There's this feature terminal right here, and maybe you don't want to use Neat agent. You can just do Claude, launch Claude, then Claude will launch, and you can do whatever you want with Claude. Change model, select which model you want to use, then talk to Claude. Hello, just say hello, and then it does that. You can do your thing while it does its thing, right? Oh wait, I need to move for. Okay, that's a bug. Yes. Okay, so I need to handle that. I found a bug. No. Okay, so that's it. So proposer is running in a sense. So proposer will just go through the system and propose. So far proposers have finished. They'll propose what to be done, what to refactor, which one needs refactor, and once all the proposals have finished proposing, the judge will run and make a judgment of which proposer to be picked. Yeah, great. So that's one. That's like this interface. We have another interface where if you just want to run agents, you don't want to like deal with an editor or just watch stuff, right? Or you just want to run multiple panes, you can do knit and launch multi-pane. I think it's multi-pane. Then I just want to do 9 of those. Or you can do whichever number you want to launch, maybe 16. 16 will launch 16 panes. And from that, you can select which agent you want to run. Say I want to configure just lab, and then I want to run um, this uh, uh, codex, and then I can tell codex what to do, right? Maybe hello, and then it will work, do its thing, and then go to another pen. You maybe launch Claude and say hello, and then go to another pen, launch Claude point 6, and then say hello. Like this is the multi-pen. Like you can do so many things with multi-pen. And if you don't like, you don't want to deal with it, you also launch the terminal here. Say you just want to Claude around here and talk to Claude, right? Hello. You can also do that, and you can switch around the pens using tab. And one other thing I want to show is if I maybe let's just launch 6 or 9. If I say maybe pick an agent, then I say there are hints here. You can say control forward slash will open the search directory. So say uh, you want to open a different directory. Say, let me see. I want to go back and back and back and back and back and what? Where was I? And I'll say dot. So I just want these directories, right? It will open that directory, and anything you do here will be in that directory, right? Anything you do with these agents will run in that directory. So you can do that and maybe switch to another project. Say you want um, to run in what so far you want to run um, maybe in this project. You can do that. Say hello, hello. So that's for multi-pane, right? And what happened generating? Yeah, so the artifacts can also be opened. And if you just want to use the terminal, you can also launch a terminal using Control Shift T. And then here it will launch a terminal. I think it launched, yeah, whichever this is. Then move language. Yeah. So that's the multi-pen. And um, the research for the research case, say you want to do research, right? Maybe I want to research. Did I pick research? Let's see. Uh, Control. Do I go back to? I forgot. Escape. No. Agents. Okay. Control R. So if you just want to select research, computational research, and then say Opus 4.8, you can launch agents to do research for you. Research, say research, how do I research? Okay, research is not written. Okay, research. Um, Okay, bulk registration. Then maybe Swarm. I can launch with using swarms. Swarm at Swarm 10, right? And if I do that, it will launch 10 agents. So 4 plus um, 4. And then it will do research. And then maybe you want to also do another research here. Say, come on, research, um, at some research on 6. Still working here. Research um, directory that's selected. Cyclic graph. Then launch them. So you launch them to the research. Once it's done, you can do other things. Maybe now program, look at the judge. All the proposals finished here. You can look at the with potentially good proposal. This looks okay. I mean, it changes, it splits the file into Cloud pool directory and then creates pool worker, even the tests, which is good. What about this? This is just single file. Let's see what the judge would pick. Sometimes it just it looks as the file and it's not well, it's a lot actually. This needs a refactor. I'll pick the split version. Let's see what the judge picks. And let's see, are we good in on time? We have can do 10 minutes. So that's let the agent finish. And these are doing research. While it's doing research, you can do other things here, maybe um I don't know. Uh, yeah. Okay. Hello. So this is a computational research investigation into bulk orchestration of multiple agent research workflows, surveying prior art and modeling execution, cost and reliability trade-offs, then synthesizing a ranked strategy recommendation persisted to a markdown file. So this is the research and then the plan, role mixed, single writer. Obviously, in research we need a single writer, and then it will put all the research found in bulk orchestration.md. DAG. Oh, again, I mean, there's one. What about this DAG one? Research-directed acyclic graph is a topic investigation mission in the lab template. So I'm running it as multi-lens survey evidence comparison, synthesized rank, and 3 parallel proposals, which is fine, reads through the system, one computational researcher, then one judge, and then one integrator, and .tmd will be written. So once the research is done, they'll write their research into .tmd. You can read the research and whatever you want to see. And I think something happened. Did something happen? All right, so something did this finish? Still running. Yeah, it's still running. I need to fix this bug. Oh, it's still okay. This is returns token cost computational. This is a proposal. Oh no, this is this computational research. The reverse token model. Um, okay. But lenses, so you can look at lenses, token budget, and topic API. Oh, this is mostly I decomposed bulk research primitive. What's this? Computational research. Okay, what about this? Again, so the judge is still running. Has to go through all the proposals, do the judgment. Anyway, so so I think that's like the introduction to NEAT. It's a lot, and I encourage you to read the blog, which explains a lot more than what I just did. You can um, you can go through the docs. So docs are in the net. We have docs for everything, like key bindings. If you are a Vima, you can see all the key bindings that are used in net. You can also look at how the terminal is set up, the substrate performance, and then security, why you need to secure. You can go through this. And swarm is how you invoke the swarm with swarm command, and you can include the mission in the prompt. Then living system, which talks about signals, or how they communicate with each other, agents communicate with each other, claims, assumptions, generations, etc. All that. And um, what else can we look at here? Uh, Coordination roles. I think we talked about this. To get more information, just go to the docs. Shadow agents, interesting feature for augmenting your prompt if you're running a single agent. For example, this didn't need any augmentation. Wait, where is it? The research didn't need any augmentation because it's a research, so the agents will figure out and just go through the plans, figure out how to do the research. And I think I found a bug. I can't scroll about here. No. Hmm. Okay, let's see this. Uh, so disagreements between lenses resolved explicitly. Was this the judge? So the judge uh, took the all the agents that were going through the lenses of the research. This was bulk orchestration. Then the frameworks comes up with systems that uses bulk orchestration like LangGraph. LangGraph is a good system for doing mostly what need does. um LangGraph, did I write it right? Yes. Agent orchestration framework. So LangGraph is one of um the best. And then cost scaling, harness default, where it spends marginal gaps. It talks about the gaps left unverified by every lens, and then goes on select guidance, suggestion, verification steps, and mostly I'm interested in the research. Let's see the research. This guy did a method probability in convergence reasoning, which is it did a quantitative convergence analysis of bulk sum integrate stage. reliability convergence sources. It refers to like Feleji and Santa theory for record linkage, and also talks about other people who have talked about bulk orchestration. I wonder if um, yeah, so Capone collector problem, expected round. So this is like probability theory, uh, consecutive empty rounds. So these are reference to some of this method. Null survivor filter. What's this? This is a skip on or skipped agents to now the integrator does that. Oh, wait, this is about provisioning data across overlapping surveys. Better than fixed estimate convergence current guarantee verification assumptions agent error skip rate. What the hell is this? Highest impact fuzzy canonical data backstop budget aware degradation with logged gaps. Uh, keep vehicles high. I mean, these are good stuff you can read, go through once the research is done. But once it has finished the research, it will write to, yeah, it did write to a file. So I'll just go through that file. Can I get it here? No, I'm not. I'll try to find that file. That's one problem. Which file is that? I'll open with Nate. Open docs. What's in docs? Yeah, this is bulk orchestration of research agent swarms, consolidated research deliverable, synthesized for independent analysis lines. So I think uh talks about the sources, all the sources, and then goes on to execution through scheduling foundations. Okay, core formulas, back of envelope numbers. I don't know what that means. Token budget, source references, Anthropic API pricing, prompt caching, token docs, etc. Quality model, diminishing returns, marginal convergence, um, optimal budget, reliability slash convergence, QC patterns. What is QC for the single writer integrator stage notation agent independent failure skip probe by finder detection? And so says convergence crux. What's that? Loop until dry termination probability of k consecutive empty rounds while t true. Okay. Verification notes or provisioning. I mean, these are like mostly just talking about um the things that exist. I mean, the research that exists, not really telling you how to use them, right? Verification notes, maybe it does. You need to go through it and um, figure out whether it does and what else did it finish? Yes, it did. So what's this? This is loop seed. We did Doug. This is Doug. I'll say which one was it? Where was it saved? I don't know. It has to be. Oh no, that's a problem. Research. Oh, I ran it differently. Okay. DAG, a synthesis of four independent research lines. theory A, algorithms B, applications, and what's this? And C, complexity, empirical measurement. So all these things were studied in DAG. So the agents produced um, load-bearing theorem, algorithmic precondition, enabling property in every application domain, cheapest measure, measured operation, topological sort is the empirical baseline against what? Against which all other costs are. Okay. Let's go to definition and foundation properties. Core algorithm with complexity. This is length D and C and D, B and D reconciled. All graphs below V vertexes and edges stored as adjacent C list. Just adjacency matrix and list. Um, the only same choice for sparse DAGs, C5 for the representation verdict. What a topological counts in degree. I think I've read about this guy, counts. Maintains a frontier of zero in degree nodes. So this is the algorithm, Khan's algorithm. Number of gametes and queued. The DFS, depth first search. We needs using DFS actually to do the DAG system. Um, cycle detection. This is interesting. And then interesting stuff. And then we have those, you know, references. But that's just to show how, to use Neat and use your agents. You still have more spaces. So if you have more projects, you can still spin them up. But I shall work on this UI. Um, what happened here? Claude Sonnet. Okay. And then last but not least, we are 6 minutes what? Ahead of time. Go through the materials, start with the thesis here, talks about everything. And interestingly, this wasn't mentioned in those agents research, because, but I think Stephen's Stephen Wolfram's work is different, a bit different, because it talks about in some role-based orchestration and ensembles, assembling of rules, picking the best rules out of the ensembles, and mostly focuses on biological systems. I don't know, um, but it's one of the places those ideas, the idea of bulk orchestration came from. But or how do you use bulk orchestration to orchestrate agents? And you can also read about stigma G. Stigma G is an interesting idea where agents, what is the alternative for agents to communicate without, a messaging channel? So that's using stigma G. Stigma G is studied, and I think it's an interesting way for agents to communicate with each other. And Nate uses that. Oh, I didn't show that actually. I didn't show that. So let's say I'll just launch, was it sub? Okay, so this is the substrate. So these are the markers agents live in the environment. So we have claims, assumptions. These are claims. So if an agent claims a file, it will it will report here. Assumptions, no assumptions. There are more signals in the environment for this many agents. So agent 0, clone 01, clone 2, clone 5 has left markers, done markers. The done marker just means that it completed work. And then we have claims, claim exclusive right. So this agent claimed this file, and then this agent claimed this file. This agent claimed this file. So if any agent tries to claim this file other than clone of 5, then what will happen is we'll see in the signals, you'll see right now we don't have, but you'll see is if did we run in parallel, yeah, you'll see another marker saying claim violation. So claim violation is an agent has violated the claim of another agent. So that's one scenario. Okay. Oh, and so to see the genome retry in action. So if a genome fails, you see this blot. It says blot in this file, which means that either that file has the agent wrote appended comments and doc strings, and then it gives the consistency of that score and the tire. The tire is two, which is two is usually spaceship, or is it spaceship? I think. Yes, I think it was spaceship or which tire was that? Where is it? Oscillator. So this was oscillator. And so it fails. This failing blood. So this file is failing. So the agent has to try. It tried, second try, and then we have three tries. We only give the agents three tries because um because of tokens. But let's reload here. Oh, the judge picked so this is the refactored version, and we can just go through the pools and see like what the agents did, and see that here it's an oscillator and consistency. Oh, this is just one file. Okay, you can see the measure of that file, and it reduced the file to just to 55 lines of code. Let's see this guy. So this is claiming to be a blot so much. So here, I'm guessing it's just these comments unnecessary. Also, I don't know whether we need these things here. Each slot. That's the fun bit, and you can read the code the agent has done, and also if you don't like it, you can just remove stuff. Now, what we need to um I don't know. I don't think we have anything to look at, but so this is yeah, blood. This is blood. Comment. It's claiming this is blood, which makes sense. Let's look at Waka. Waka is fine. Looks clean. This is the Waka, and nothing bad. Function. 285 lines. Not bad. So from around 1800 lines of files, it reduces to a small number. And so this agent did retries, two retries, and the other agents, which is this, failed again because it worked on pool. it failed, and now it's retrying, and also agent 5 is retrying on Waka. I don't know, I need to update. Okay, so yeah, let's close these. And I think that's it. I mean, this was supposed to be a 1 hour stream, but oh God, it went overboard. Went um. All right, so let's finalize this. We've talked about um nothing interesting here. Just the site, and then thesis. You can go and read the thesis, comment, and the demo. And we've gone through the demo, and we have run some agents. We have seen the retry. We have seen how they grow, the score changes. So if an agent edits a file and it degrades the quality, you'll see that marker here. And that is if that file that the agent is working on is open, right? And then we have also seen this structure. You can see the structure of this file, right? And we have also run a simulation of that structure and seen an example of a cellular automata running. And you can see which role is running and which encoder is being used and etc. etc. And what else? So far, I haven't really. Wait, I have found some interesting structures, but um, not very much, very interesting. But one thing I want to say is if you in we have um when you run a game of life sort of simulation, we store the data. You can find the data in goal snapshots, and you can study it. You can do um goal uh what come on, where is it? You can study this file, what what changed, which token encoder, which encoders param, the mirror, the density, the input hash, so that you can reproduce the same structure and width, height, all that other stuff. Okay, so that's it, and thank you for watching. Um, we will be we will be talking more about uh, coming up, new coming features. For example, we have uh, another feature coming up, which agents are working together. But what currently we don't have is for agents to, compete. So if you put two agents together, they compete to work on a file, and whichever, but we don't have sort of that uh, what we can score against. Like if you put two agents to compete on solving a certain problem, what then do we what then do we score the agents? Like what is the payoff in a sense for those agents so that we can select the winner? So that's not something easy, but so that's something we are looking into, and we are working on lean, neat lean. So um, if you are a researcher, mathematical researcher, or proof researcher, you might certainly have used Lean. But um, and there are systems like anti-gravity which has inbuilt Lean proof systems, so you can do proof assistance using Lean. So we want to add a way for when you select a mission right here, like say research, we want to also include um, proof assistance research or proof Lean proofs so that you can ask Neat to do some sort of ask Neat Lean to do proofs or to measure proofs or verify proofs or do all those uh, proof things. Give Neat a theorem, and then it produces a proof of that theorem. And the other, I think those are mostly um, the things that we're. Oh, then there's because we are dealing with code and code measuring quality of code is good, but then there's also the question of how can do agents really write functionally uh, good code, or if the agents writes code, can it evolve the code? So like how Alpha Evolve does, we have such systems like Alpha Evolve, which evolves agents algorithm code written by agents. They can evolve their code and pick which code is good based on the evolution or the evolved code. There are other systems too, but most Gemini uses Alpha Evolve, I think. But if we something similar that like neat evolve would be nice so that it's inbuilt in the editor, so you don't have to you can we can add it as a template so that when you select a template like evolve, neat evolve, agents will write code and measure it against genome system, but then that that is for structural. It just measures structurally the structure of the code. What we want is can we measure the agent's actual algorithm? Like, is this can agents evolve to a point where they can write simpler but not too simple code that is functioning correctly? So sometimes you'll find that agents write, a block of code like I mean 20 lines of code, but somewhere, somehow in the system, you'll find that in the search space, evolutionary space, you'll find that an algorithm exists can that can be reduced into just 5 lines of code that does the same thing. Now, can agents can evolve to that, so to write that piece of code or to find that piece of code. So that's one thing we can explore, but that's sorry for another time. For now, if you have any, if you're interested, you can just install Neat. It's free, uh, distributed via downloads, and then just look at this stuff here, and figure out how to use them. And if you find bugs, we have Discord channel. You can report bugs there. And the genome challenge is not live, but it's just displayed here. This will be like a way for people to share their um, their hashes, so reproducible hashes, like what we saw here. If you reproduce something like this, you run a snapshot, find interesting structures, you can share those structure via this challenge, and maybe your code as well, and people can reproduce those structures, give them names, and what we want is to be able to fill, because Conway's website has many of these structures, but Net can be a way to find such. This is a glider. Net can be a way to find such structures. We've seen this structure while running Net simulation, but when how many do we have? I don't know. This is just for play. Yeah, this is the website. So structures like these. So this is like one structure. If we find this structure or this, or interesting structures like these, then we can post them on Neat Challenge and um, tell us about the code that produced that. Can also go to Conway's Game of Life and see what has been done before and what exists currently. Discovered wiki. Um, yes. All right. And the fun bit is you can change the theme. All right. Let me close it. Anyway, so thank you for watching, and be sure to install it when you feel like it's something you can use. And then we can talk about coming features and bug fixes along the way because the more you use Neat and code with Neat, the more you capture these bugs, and that's what we want. And thank you, and see you next time. Uh, Closing stream.